in vacuum, divergence E equal to 0. Okay, so these are the four equations, and Mr. Maxwell was going to see what these equations predict. Okay. What kind of electric and magnetic fields exist in vacuum, can exist in vacuum. Okay. So, um, so by the way, so we'll just mention a couple of things about it. So this equation tells you time-varying electric fields are producing magnetic fields, and this equation, which is Faraday's law, is telling you time-varying magnetic fields are producing electric fields. Okay, so let's see how these look like. Okay, so let's see what kind of electric fields the time-varying magnetic fields produce. You've seen this before already, and what kind of time-varying electric fields produce magnetic fields. Okay. So we'll see that. Okay. All right, so this is showing you the following. So if a magnetic field is increasing like this, it'll produce an electric field like that. Okay. So that's what Faraday's law says. Okay. Increasing magnetic field in this direction will produce an electric field like that. And the next diagram shows you an increasing electric field. So when you're charging a capacitor, the electric field, so this is one place you encounter this time-varying electric field. When you're charging a capacitor, the electric field between the capacitor is increasing, and that increasing electric field produces a magnetic field like that. Okay? And that's what these two equations are telling you. Okay? So now you have a picture of, so a time-varying electric field produces a magnetic field like that. And how far does this magnetic field go? It goes all the way to infinity. Okay, so it's time-varying electric fields, the magnetic field, the effect is going out at the speed of light anyway. So that's the magnetic field produced. Okay, and increasing magnetic field in this direction is producing an electric field like that. All right, so now let's study these equations in vacuum. So this term will be 0, this term will be 0. That's what I've written. So Maxwell, using the four equations, predicted the existence of electromagnetic waves that propagate through vacuum at the speed of light. So he's going to study these equations in vacuum. Okay, so there are the equations in vacuum. There's one thing you'll need for what he did. Here's this vector field identity that you'll need. Okay, I don't know, maybe you will see this in Calc 3. It says curl of a vector field is equal to gradient of a divergence of the vector field minus, this is called the Laplace operator, Laplacian of the vector field. All right. So again, let's make sure of a couple of basic things. Okay. I'll write down the definition of all these guys. Has anybody seen anything like this in classes? Okay. All right, I'll write down the definition. Okay. So let's first make sure. Okay. Curl of a vector is a vector, and curl of that vector is a vector. So on the left-hand side, you have a vector. So what you need is vectors on the right-hand side. Divergence of a vector is a scalar, and gradient of a scalar is a vector. So this is a vector. and the Laplacian of that is of a vector is a vector field. Okay, so let me write down that identity, and we'll use that identity. Okay, so curl of a curl of a vector field is gradient of the divergence of the vector field minus del square A. Okay, now let me write down the definitions. So curl of a vector field, you already know this. This is a, so the x component is del y az minus del ay plus the jth component is del z by ax Okay, so that is the definition of a curl of a vector. Okay. Let's do the next one. The divergence of a vector field. Again, you've seen some of these pieces. The only piece you haven't seen is this fellow. Okay, and I'll come to that in a second. Divergence is del by del x. Divergence is just like a dot product. Okay, so del by del x ax plus del by del y ay plus del by del z az. And del square A is just, this operator is the following operator. And you're taking it on that vector. And let me write it like so. Ax I plus ayj plus az k. Okay, so what you're doing is taking this operator acting on ax. Okay, so let's make sure you understand that. So that's del square by del x square ax plus del square by del y square ay plus del square by del z square a. I, and so on. See, this operator acting on ax, I, and this operator acting on y, j, and so on. Okay. So that's the y component. I'll write it like so. Ayj plus del z square azk. All right, so here again, I don't want you getting lost in the technical details. So what we are doing is the following. Mr. Maxwell is studying these equations in vacuum, and we are trying to find out what kind of electric and magnetic fields can exist in vacuum. Okay, and all we're going to do is use this vector field identity. Okay, and the vector field identity says curl of a vector field is equal to gradient of a divergence of the vector field minus this Laplace operator times acting on the vector field. The curl of a vector is given by that. Okay. The divergence of a vector field is given by this. And here is the Laplacian on that vector field. All right, so let's do this. Okay. Okay, so let's closely. So what we're going to do is we have this equation. Curl of a vector field is minus del B by del T. All right, so what we're going to do is hit this guy with a hammer. What did we do? We took the curl of this left-hand side. So what you have to do, you have to take the curl of the right-hand side. So that's equal to curl of this minus del B by del T. All right, now here's the basic rule. So if you're taking partial derivative of a function of x and y, del y, these derivatives are interchangeable. You can take the derivative with respect to x first, and then take the derivative with respect to y. Okay, you guys all know that rule. Okay, so similarly, you can interchange these. So you can take the curl first and then take the time derivative. This is equal to minus del by del t of curl of b. Okay. All right, well, curl of B, what is curl of B? Curl of B is equal to that, is equal to a time derivative of the electric field. Okay, so this is a very fundamental discovery that Mr. Maxwell made, and this is fairly easy to derive. So it's minus del by del T of epsilon naught mu naught del E by del T. Okay. This is equal to minus epsilon naught mu naught del square E by del T. All right, what is this? We are going to use that vector identity for a curl of a vector field. Is, remember, it's gradient of the divergence of the electric field minus del square the electric field. And that is equal to minus epsilon naught all right, so let's look at this first term. Let's go back to our Maxwell's equation. In vacuum, divergence of electric field. If there's an electric field in vacuum, its divergence is 0. So this guy is 0. So what you have now is del square E equal to epsilon naught mu naught del square E by del T squared. Okay, of course we'll cancel out the minus signs, so we'll just write it like so. Del square E equal to epsilon naught mu naught okay, it turns out that this has dimensions of 1 over velocity squared. And we'll call it V square for now. All right, so now let's just mention a couple of things about it. Remember, del square was the Laplacian operator. It has, so it's del by del x square, okay, plus del square by del y square plus del square by del z square E equal to 1 over V square okay, so let's point out a couple of things. Here is an electric field divided by distance squared. Okay, see delta z is a distance and delta z squared is a distance squared. So on the left hand side, what do you have? An electric field divided by distance squared. And on the right hand side, you have an electric field, and velocity times distance is velocity times time is distance. So velocity square times time square is distance square. So dimensionally, this equation is correct. Okay, what else do you see? So this equation relates a second spatial derivative to a second time derivative. This is called a wave equation. Okay. And you've seen this before for mechanical waves. So this is a wave equation. Okay. And what it predicts is traveling waves. Okay. So Maxwell's equation in vacuum predict if there exist electric and magnetic waves, they're traveling waves. Okay. So that's what these equations predict. Okay, now we derive this equation for electric fields. You can do the same thing and derive an exactly same equation for the magnetic field. Okay, so you'll get exactly the same wave equation for magnetic fields. Okay. All right, now we're looking for solutions. Look for solutions to these equations. Okay. Now, this is, again, let me write this equation out. Del square del x square plus del square All right, this looks pretty messy. Okay, so of course, what do? You make simplifying assumptions. So let's look for electric fields that are only functions of x and t. We'll look for solutions that are only functions of x and t. Okay. You're always making simplified assumptions, so these two terms will drop off, because this guy doesn't depend on y and z. So what you have is del square E by del x square equal to 1 over v square del square all right, and the solution to these guys are easy to find, and so this is a solution. Ex of t equal to E naught, the amplitude sine or cosine x, cosine kx minus omega t, okay, where omega over k equal to v, that v in that equation. Okay, so here is this is a sine wave traveling to the right. Okay, and then you can have solutions with plus, you can have solutions traveling to the left. Okay, and so here is how the solution looks like. Yeah, so here is a sine and cosine wave. Here is a traveling wave traveling to the right. Okay, and it turns out that because E and B are related like this, it turns out that when the electric field is like this, the magnetic field will be like that, perpendicular to it. Okay, and so that's the solution. So you get this solution for the electric field and an exactly similar solution for the magnetic field. Okay, so magnetic field will be B naught cosine kx minus omega t. Yeah. And again, v equal to omega by k. So what you get is traveling wave solutions of electric and magnetic fields to the Maxwell's equation in vacuum. And here was the surprising part. This velocity, okay, this velocity, that's the velocity of the wave. And that turned out to be exactly the, hello there?
I'm sorry, it's becoming emergency.
So this, it turned out that that measured the velocity of light. And here was a wave whose velocity was exactly equal to the wave, to the speed of light. That was the first time they realized that light was an electromagnetic wave. Okay. So again, we did a lot of technical details. So let's go over it again. What is Maxwell doing? Studying these equations and studying these equations in vacuum, and he looks for solutions in vacuum, and what he finds is that both the electric and magnetic fields have to satisfy the wave equations, and these wave equations are predicting traveling waves solutions. And so people went looking for them. So it predicted this. This is the simplest equation, plane wave equation, and so people went looking for them. And Mr. Hertz, after whom we named the unit Hertz, he did the experiment. So here's the wave equation, and I wrote v squared there. That's the speed of the wave, and it turned out that speed of the wave was exactly equal to the speed of light, and that's when we realized that light waves are electromagnetic waves. Okay, so to detect these waves, okay, so let's look at the properties of these waves. The direction of travel, both the electric field and magnetic field are perpendicular to the direction of travel, and the electric and magnetic fields are perpendicular to each other. So if a light beam is traveling like this, and electric field oscillates like that, the magnetic field oscillates in a perpendicular direction. Okay. For the light that you can see, for visible light, the frequency is about 10 to the power of 15 hertz. That is, if the electric field is pointing in this direction, then it goes down and then back up. That's one oscillation. Okay. So for visible light, the frequency is about 10 to the power of 15 hertz. Okay, so everything is happening very fast. Yeah. All right, so there's the traveling wave, and of course you can have waves travel to the left and so on. Okay, the speed of the wave is omega by k, or frequency times lambda. All right, so Mr. Maxwell predicted these traveling waves, okay, waves that contain both electric and magnetic fields, and that's why they're called electromagnetic waves. And all waves carry energy, so we're going to test this. We're going to look for these waves. And this was the setup. Okay, so here's an RLC circuit. You know that the LC circuit oscillates, and the resistance is it converts energy into heat. So this AC source is pumping energy into the circuit, and if its frequency matches the frequency of the circuit, it can set up large amplitude currents, and then you couple this inductor to that inductor via a transformer. So this is an LC circuit. This is like a capacitor. This is an LC circuit. All right, so this circuit is transferring energy here, and this circuit is radiating the electromagnetic wave. And you catch this electromagnetic wave through another another capacitor, another tuning circuit, another LC circuit. All right, so the frequency of this matches the frequency of this guy, which matches the frequency of that guy. Okay, so that was the setup. So, so here's a high voltage source. Okay, so this was the transmitting capacitor, and here's the receiving capacitor, and this is not connected to any source. And when this grabs that electromagnetic wave, a spark is generated here, and so this is catching that energy. Okay. So here was a wireless transmission. Here, this was the first wireless transmission. This is Mr. Hertz's experiment. Okay. Again, this source is pumping energy into this circuit, which is into this LC circuit, which is radiating it, which is caught by this LC circuit. Okay. So again, Mr. Maxwell's equations implied traveling electromagnetic waves, which Mr. Hertz detected. And once these, so this was the first time when we realized light was an electromagnetic wave. And the reason we realized that was because Maxwell's equation predicted traveling waves, electromagnetic waves, whose speed was equal to the speed of light. Okay. All right, so now here are some properties of electromagnetic waves. Okay, so here's a plane electromagnetic wave. So it's called a plane wave because if you draw a plane perpendicular to the direction of travel, okay, in that plane, the electric field is constant everywhere, and the magnetic field is constant everywhere. So that's the solution we found. You can go anywhere in the wave. So let's say we stand here, we measure the electric field and we measure the magnetic field. The ratio of the electric field to magnetic field is equal to the speed of light. So you can go anywhere. Okay. And so that's true for the maximum value of the electric field divided by maximum value of the magnetic field is equal to the speed of light. Yeah. So at every instant, the ratio of E to B fields is equal to the speed of light. So here are the properties of electromagnetic waves. Both E and B fields satisfy the wave equation. In vacuum, they travel at, all electromagnetic waves travel at 3 times 10 to the power 8 meters per second. So what are the kinds of electromagnetic waves you know? Okay, so here's the electromagnetic spectrum. Okay, so visible light, UV light, X-rays, gamma rays. You see, this is the shorter the wavelength, higher the energy, and all these waves travel at the same speed. Okay. Radio waves, microwave, infrared waves, they all travel at the same speed, 3 times 10 to the power of 8 meters per second in vacuum. Okay. In a plane wave, E and B are perpendicular to each other and to the direction of propagation. So they're perpendicular to each other and to the direction of propagation. Okay. This ratio is always C in vacuum. Okay. In a piece of glass, that's not true. In a piece of glass, that's equal to the speed of light in vacuum. I mean, in the piece of glass. Okay. So They obey the principle of superposition. That just means that if you have one beam traveling like this, another beam traveling like that, and when they meet, to find the electric field, you just add the electric field of this beam and the electric field of the other beam. Yeah, so and similarly, you just add the magnetic fields of the beams. Yeah. All right, here are just some typical numbers for a radio wave. Okay, so FM radio, for instance, is in the frequencies in the 100 megahertz range. Okay, so here's a radio wave whose frequency is about half the frequency of FM radio. Okay. And remember the speed. The speed is frequency times wavelength. Okay. So as the frequency decreases, the wavelength increases. Okay. So for this guy, the wavelength is about 10 meters, 7.5 meters, about half the width of this room. Okay. So for FM radio, the wavelength is about 3 meters. So FM radio has wavelengths about the width of this table. Okay. The amplitude of the field, the electric field, is 750 Newton per coulomb, or 750 volt per meter, and the magnetic field is that strength, and that's about one tenth the Earth's magnetic field. Okay, so that's the strength of the field. Okay, all electromagnetic waves carry energy. So let's say a beam is traveling in this direction. What you want to know is, okay, intensity is equal to energy per unit area per unit time. So what you want to know is how much energy is passing per unit area per second, and that's intensity. And intensity, Mr. Poynting derived this formula. So this is called a Poynting vector, denoted by S, and it's 1 over mu naught E cross B. Okay, that's how much energy is passing per unit area per second. Of course, in that invisible light, how fast is E changing? What is the frequency of E? About 10 to the power of 15 hertz. So things are changing very fast. Okay, so light, the instantaneous intensity is changing very much. So most of the time we're just interested in the average value. So S, the average of the Poynting vector, is just the amplitude max divided by root 2, max divided by root 2. Okay, so max divided by root 2 times max. Yes. So there's the average intensity. All right, so what you're interested in is, so this gives you the average intensity. Okay, now if you think of a pencil of length C will pass through this in 1 second. Okay, so the intensity is given by the speed of light times the average energy per unit volume. Okay. So you can take a unit volume, 1 meter cube, and the energy contained is in this times C passes through. So that's the energy density in the electromagnetic field times the speed of light. And so this energy density works out. You can express it in terms of either the electric field or the magnetic field. So what this means is, okay, so let me shine my laser here. So what that formula means is the following. Okay, so if you can calculate the intensity, you can take the energy content of a unit volume of this beam. Okay, so the energy content in that beam, you can measure the maximum electric field, and that will give you the energy per meter cube. Okay. And a meter cube is this much. This is a meter cube. So if the beam was that wide, that's how much energy there would be per meter cube. Or you could calculate the energy in terms of the magnetic field. Okay, so now let me first give you a mechanical example. What is the kinetic energy of a moving object?
1/2 mv squared.
1/2 mv squared. Okay. What is the momentum of the object?
mv.
mv. Okay. So you can see that the momentum is energy divided by velocity, except for this factor of half. Okay. So anything carrying energy should have momentum, carries momentum. So you just saw that light carries energy, so it must have momentum. Okay. So the momentum carried by a beam of light is the energy in the beam divided by the speed at which it's traveling. Okay. So the momentum carried by light is the energy divided by its speed. Okay. Now, back then, when they found all these formulas, they didn't know that now, like we do now, light is a stream of photons. Okay. Yeah. And just like when you hit something with a bullet, you transfer momentum to it. Just like that, when something absorbs a photon, you transferred momentum to it. And if it reflects, then you transfer twice the momentum. Okay. Anyway, so the momentum carried by a beam of light whose energy is u is that much. If the surface reflects, the momentum transferred to the object is twice as great. Okay. So if the light bounces off, then the momentum is twice as great. All right, so light either absorbed by a surface or bouncing off that surface can exert a force on this object. So let's say can exert a force on this object. Force, so pressure is force divided by area. So here's 1/area. Force is rate of change of momentum, rate at which momentum is transferred, and momentum is energy. So here's 1/area, energy divided by c. So du by dt times c, and this guy is the pointing vector. So the pressure that a beam of light exerts on a surface, this is when it's absorbed, is the pressure exerted by a beam of light is the intensity divided by c. Now this is for real. For instance, see, here is a solar sail, and this is sunlight exerting a pressure. Now the sunlight is bouncing off, so the pressure exerted there is twice S over C. And this is going to push the solar sail to whatever destination. Okay. And this is for real. So for instance, if this solar sail was as big as our campus from White Street to Dunn to Clyde Morris, and if it weighed 1,000 kgs, it would get from Earth to the moon in 10 days, 11 days. Okay. So it can get there quite fast in realistic time. And here's another evidence of the pressure, radiation pressure, this radiation pressure. Okay, so here is the sun. What is the sun emitting?
Light, photons, electromagnetic waves.
Yeah, so protons and electrons escape as well. And most of its energy is coming in photons. Okay, so here's a comet where stuff has evaporated, and some of the stuff has been ionized. Okay, some of the gases has been ionized. The solar wind repels these ionized gas, and the photon, and these are neutral particles, just dust particles, and the photons are pushing these neutral particles. Okay, so here's evidence of the pressure that photons exert on these neutral particles. Okay, so a comet will have two tails, a gas tail, which is of ionized gas, and a dust trail, which is neutral particles which are blown by the photons, by the electromagnetic waves. Okay. And again, here's solar sails, which utilize the pressure of the electromagnetic waves. Okay. And here's the electromagnetic spectrum, and again, arranged in order of shorter wavelength, and this is higher energy. Okay. We have electromagnetic wave detectors. Your eyes are electromagnetic wave detectors, and your detector work in this small window. Your detector cannot detect any of these wavelengths. Okay. These wavelengths could cause damage inside your eyes, but your nerves would not be triggered by these wavelengths. Okay, there would be no signal in the optic nerve. Only these wavelengths will trigger a signal in your optic nerve. Okay, because that's the photon sensors work only in this small window. Okay. And here are various uses we use. So if you use wavelengths of that, you can use, those are X-rays, you can use, you can take pictures like that, and so on. Okay. So at various wavelengths, they show you the technologies that we use. Okay, so this is the small window we are sensitive to. So that's the visible range. And the shortest wavelength where we can see is 400 nanometers, and the longest wavelength we can see is 700 nanometers. So roughly that is the range we are sensitive to. And again, our sensitivity is not uniform. Okay. Our eyes are most sensitive to this wavelength. Okay, so this is relative sensitivity. Okay. So we are most sensitive to yellow-green, 550 nanometers. That's why tennis balls are colored that. Okay, roughly. Right. So what this graph is telling you is, if you send yellow-green of that intensity and this wavelength of same intensity, the current is that high for yellow-green and this low for this wavelength. Okay, so this shows you the relative sensitivity. You saw how microwaves work. Again, microwaves are electromagnetic waves. So inside your microwave, you have what you do is set up standing waves, and the electric field, what it does is, so the water molecule has a dipole moment. This end of the water molecule is positive, this end is negative. So here's the dipole pointing in this direction. The dipole is denoted by P. And if the water molecule is in this direction, what this electric field will do is turn the water molecule this way. Okay, it will try and line it up. It will line it up like that. Okay. And then the electric field switches, so the water molecule is shaken back and forth like that, and that's how the electric field catches hold of a water molecule and shakes it back and forth, and that's how it heats the water molecule, which transfers the heat to the surrounding material. Okay. So the frequency of the electric field in a microwave is 5 billion. Okay, so this water molecule is shaken 5 billion times a second. Okay. Here's how radio waves are transmitted. This is two pieces of metal acting like a capacitor. Here's an inductor. This has a natural frequency of oscillation. Okay. So what we're doing is, here's a AC source. It's pumping energy into this circuit, which is coupled to this circuit, and this circuit is radiating away energy. Okay. To produce electromagnetic waves, what you need to do is you need to grab hold of a charge and make it oscillate back and forth, and you can emit electromagnetic waves like that. And that's what's happening here. When this thing oscillates, this is positive and negative, and in the next cycle this will be negative and positive. So essentially what you're doing is grabbing hold of a charge and jiggling it, and you're emitting electromagnetic waves. The frequency of the wave emitted is 1 over root of LC, where L is this and C is the capacitance of that. Okay, so if you want to be a 100 megahertz FM station, this needs to be 100 megahertz. Okay, so that's what that is. So the dipole, this is a dipole antenna, radiates wave of frequency that. Okay, this shows you, so here's the dipole antenna, and it shows you, so the electromagnetic waves. So the magnetic field is into the sheet, out of the sheet, and electric fields are concentric, are in that direction. Okay. So the magnetic field lines are concentric circles around the antenna. So there's the antenna, and there's circles around the antenna. The length of the rod is equal to 1/4 of the wavelength emitted. So if you're a radio station, remember, if the frequency of your radio station is about 100 megahertz, we saw that the wavelength is around 4 meters. And so the length of each rod is equal to 1/4 of the wavelength emitted. So each of these rods is 1 meter. So for an FM station, for this two dipole antennas, so the dipole antenna is like that. You break it into half. Here's 1 meter, here's 1 meter. Okay. And so this is showing you, so there's the dipole antenna. The intensity is maximum in this direction, and the intensity is 0 in that direction. Yeah. So the intensity is proportional to sine squared theta divided by r squared. And so if this is a radio station, if you're hovering right above the radio station, you get 0 signal. Okay, so if you're in a helicopter above the radio station, you get 0 signal. Okay. You of course know that there are AM and FM radio. AM is amplitude modulation, and FM is frequency modulation. Okay, so what these have is, you have a signal. The signal is the song you're transmitting, plus a carrier wave. Okay, signal is, so when somebody's singing, what is the frequency of sound you produce? About 500 hertz. And the carrier waves are megahertz. Okay, 1,000,000 times greater. Okay, so the carrier waves frequencies are 1,000,000 times greater than the signal waves. Okay, so that's how you do. Okay, so carrier modulation. Shown are results of carrier signals being modified by signal in AM and FM radio. Okay, so this is AM radio, amplitude modulation. Okay, so here is the carriers, here is the signal. See, low frequency signal, the blue wave, and the carrier signal is the red, which is a high frequency signal. Okay, so you see, superimpose the signal over the carrier signal, and you see, so the carrier signal was that uniform amplitude, and you superpose the signal, and now The combined signal is the red signal. Okay, so that's the signal that's transmitted. And then you receive it, and then you separate this from the carrier in the radio. The problem with this method of transmission is there's a lot of noise. Okay, so random signal can cause noise, cause interference. Frequency modulation, with frequency modulation, there is the signal again, the blue signal. The green is the carrier signal. And what you do is you break this signal into frequencies and then change the frequency of the carrier signal. So the frequency is being changed. And so there's no noise in this thing, okay, with frequency modulation. The advantage amplitude modulation has is you can transmit this a long distance. This can only be transmitted short distance. So no noise, but short distance. No noise, but short distance. So for instance, you can't catch a FM signal from New York, but you can catch a AM signal from New York, because this signal can bounce off of the ionosphere. Okay, so noise, and you can catch a signal from Europe, okay, plus long distance. Okay. And again, what you're doing is trying to figure out different ways to superpose signal on a carrier and transmit it. Okay. All right, guys, so that finishes this chapter.